Hi everyone, this lesson is about implicit differentiation, and this is a technique we can use when we have formulas like this. So it's not the usual way where we write y equals and then there's some sort of an expression with x. We have here y squared, not y, and it's x squared is on this as well. And this of course is the equation for this circle with the radius 5 centred at the origin. My task today is to find the equation of this tangent line, which happens to be touching the circle at the point 4, 3. It would be easy to show that the point 4, 3 satisfies this equation. Now, how do we go about this? Well, we find the derivative with respect to x of the left-hand side. Now, we'll worry about how we do that in a moment. And we find the derivative with respect to x of the right-hand side. Seems logical enough so far. Now, as we've seen in the past, the derivative of two terms which are added together is the derivative of the first term added to the derivative of the second term. Now, the derivative of a constant is 0, so we might as well simplify that. Well, this first part doesn't seem to be too difficult. The derivative with respect to x of x squared is 2x plus something which equals 0. Now, it would be lovely if I could take the derivative of y squared with respect to y. I mean, if I could put d over dy of y squared, then my life would be simple because we can do that, no trouble at all. But I can't suddenly change d over dx into d over dy for no apparent reason. Now, those of you who've watched these things before, you'll realise I've left a gap here for some reason. What could I write here so that whatever is here multiplied by d over dy is equivalent to d over dx? Well, there's a dx in the denominator, so I'd better introduce a dx in the denominator of this factor. And there isn't a dy appearing over here, so I'd better put a dy in the numerator of this so that they counterbalance each other there. Now, that means I would have a dy over dx multiplied by, and this part is just the derivative with respect to variable y. That's 2y. That step there is the implicit differentiation. What we did here. That's the key. So if I wanted to find the derivative with respect to x of some expression involving y, I take the derivative normally. I end up with 2y, but I have to introduce dy over dx as a consequence of doing that. Now let's continue to simplify and we will isolate dy dx. Dy dx by 2y would equal negative 2x. I could divide both sides by 2y, and then of course I could cancel the 2 from the numerator and the denominator. There's my expression for dy dx. And you'll notice that it's not just in terms of x, it's in terms of y as well. So let's go back to our question now about our tangent. I wanted to know the formula for this tangent line. I know the point is 4, 3, and I know that that point belongs to the circle. This formula gives me the derivative dy dx of the circle. So here we go. At the point, it was 4, 3, wasn't it? Yes. At the point 4, 3, dy dx would be negative, the x coordinate is 4, over 3. Now that, of course, also tells me the gradient of my line. So my line then, I could use the expression y take y1 over x take x1 equals the gradient. So effectively what I'm doing, I'm imagining, what's going on there? For some reason, OneNote doesn't want to behave for me today. I'm imagining some point here, which is labelled x, y. And this one, I'm considering this to be x1, y1. So I'm effectively taking the gradient between a generic point, xy, and a point with coordinates x1, y1. So I'd have y subtract. Now my point here, the y1 value from the point is 3. The x1 value is 4. And all of that equaled the gradient negative 4 over 3. So y take 3 would be negative 4 over 3 by x take 4. Whoops, that's take 3. Y take 3, so I'd have negative 4 over 3 x. Negative by negative is positive 16 over 3. I would need to add 3 to both sides. 3 is the same as 9 over 3. So I have negative 4 over 3x plus 25 over 3. That's the equation of my straight line, my tangent, which just happens to be the tangent at that point of interest which I showed. Now that's just a way of using the derivative, but the main point of this lesson was what we did over here, the implicit differentiation. That's the main takeaway from this. The other one was just an example of where we might use it. Right, that's enough for this one. I'll be back in a moment with another example of a more complicated implicit differentiation. Thanks for watching.